Welcome, SPS Clark Grade 9 students. I am so excited to have you join me for today's Geometry Explainer. You're definitely in for a great session. Today, we're focusing heavily on exact, precise definitions and structural truths as we tackle our specific lesson, Grade 9, Geometry, Unit 4, Lesson 2, Parallelograms and Special Quadrilaterals. We've got some absolutely brilliant material to get through today that is literally going to reframe how you look at everyday shapes. Okay, let's dive into this. Here's our quick roadmap for today's session. First up, we've got our lesson objective, then defining parallelograms, followed by special quadrilaterals, the square misconception, a quick formative check, and finally our lesson recap. Let's get to it. Section 1, lesson objective. Setting a really clear goal is absolutely crucial for any successful study session. So, our objective today is to completely master the properties of parallelograms and accurately classify special quadrilaterals based on actual geometric theorems. This level of precise vocabulary is a huge deal, especially for those of you navigating the rigorous STEM integrated curriculum over at SPS. In STEM, we don't just eyeball a shape and guess. We define it by provable, hard properties. Moving right along to Section 2, defining parallelograms. All right, with our target locked in, let's establish the ground rules. By definition, a parallelogram is a quadrilateral with opposite sides that are parallel and equal in length. That's it. That's the baseline geometric requirement. Basically, if a four-sided polygon doesn't meet those specific criteria, it just doesn't get into the parallelogram club. So the crucial point here is exactly how this definition unpacks into provable theorems. According to the rigorous standards from illustrative mathematics, when we have those parallel opposite sides, three distinct theorems immediately emerge. First, the opposite sides are congruent, meaning they are the exact same length, no exceptions. Second, the opposite interior angles are also congruent. And third, the diagonals of a parallelogram bisect each other. That just means they slice each other exactly in half, right at the point where they cross. Now consider this question, and this is totally inspired by the kind of stuff you'd see on interactive geometry platforms like GeoGebra. Do the diagonals of a parallelogram bisect its interior angles? I want you to actually pause for a second and mentally visualize this. Think about a stretched out, highly slanted parallelogram. If you draw a diagonal line straight from corner to corner, does it cut that corner angle perfectly in half? Commit to an answer in your head right now. Got it? Well, the answer is actually no. While the diagonals definitely bisect each other, they don't necessarily bisect the interior angles of a standard parallelogram. To make that happen, you need a much more specific set of constraints, which leads us perfectly into our next topic. Section 3. Analyzing special quadrilaterals. Let's see what happens when we start adding more specific constraints and rules to our standard parallelogram. A rectangle is mathematically defined as a parallelogram with right-angled corners and congruent diagonals. Now, I really want to highlight that phrasing. A rectangle is fundamentally a parallelogram. It already possesses all the features we just talked about, parallel opposite sides, bisecting diagonals, but it brings a few extra VIP features to the table, specifically those perfect right angles and diagonals that are exactly equal in length to one another. And this brilliantly illustrates the whole hierarchy of geometry. A general parallelogram's diagonals bisect each other, which makes sense. But when we look at the rectangle, because we force the corners to be exactly 90 degrees, it forces those diagonals to not only bisect each other, but to become congruent. They become identically long. You can almost think of the rectangle as a more highly evolved, constrained version of the classic parallelogram. Section 4. The square rectangle misconception. Okay, now we arrive at what I like to call the narrative climax of today's explainer. We're about to completely challenge a belief you have likely held since you were in kindergarten. Ready? Is this square entirely different from a rectangle? I'll give you a beat to think about this. If someone hands you a wooden block and asks if it's a square or a rectangle, you naturally assume it has to be one or the other, right? Let's take a look at the geometric reality. Listen to this brilliant insight from the educational experts over at Maths No Problem. They say, when we say square, we use it as a noun, when in reality, square is an adjective that describes a type of rectangle. I mean, let that geometric mind-blower sink in for a second. We've all been so lazily using square as a noun our whole lives, but geometrically speaking, square is just a descriptor. The technically correct term for the shape is actually a square rectangle. Mind blown. Let's break this analysis model down so it really sticks. Think of rectangle as the family name. It's the broad umbrella category for any parallelogram with right angles. Now, within that family, we have two specific first names. First up, the square rectangle. This is a rectangle that is equilateral, meaning all sides are equal, and equiangular, all angles equal. Plus, its diagonals uniquely cross at perfect right angles. Then, on the flip side, we have the oblong rectangle. This is your everyday non-square rectangle, where one pair of parallel sides is longer than the other. So ultimately, a square isn't a completely different shape from a rectangle at all. It's just a highly specific, special kind of rectangle. Section 5, quick formative check. All right, let's jump into a super quick active recall exercise to solidify this newly updated schema of yours. I want you to evaluate these three statements mentally. Number 1, true or false, every square is a rectangle. Number 2, true or false, every rectangle is a square. And number 3, true or false, the diagonals of a rectangle cross at right angles. Go ahead and lock in your answers. Let's walk through these together. Statement 1, every square is a rectangle. That is absolutely true, because as we just learned, square is literally an adjective describing a specific type of rectangle. Statement 2, every rectangle is a square. That is false. Why? Because oblong rectangles, those tall thin ones or short wide ones, definitely exist and they do not have 4 equal sides. Statement 3, the diagonals of a rectangle cross at right angles. That one is also false. The geometric reasoning here is that an oblong rectangle's diagonals do not actually meet at 90 degrees. Only the diagonals of a square, rectangle, cross at exact right angles. How did you do? Finally, Section 6, lesson recap. Okay, let's move to our rapid-fire core takeaways to lock all this in. Number 1, parallelograms feature congruent opposite sides and angles, and their diagonals always bisect each other. Number 2, rectangles are parallelograms that take things a step further by adding perfect right angles, which automatically forces their diagonals to become congruent. And number 3, our big revelation for the day, square is not an isolated noun, it's actually a descriptive adjective used to define a very specific rectangle that is perfectly equilateral and equiangular. I want to leave you with this final, somewhat provocative thought. As SPAS Clark Grade 9 students diving deeper and deeper into advanced STEM, how will treating square as a descriptive adjective rather than an isolated shape completely change the way you analyze geometric proofs in the future? Think about how recognizing the shared DNA between these quadrilaterals gives you so much more mathematical power. Thank you so much for joining me in this explainer. Keep asking brilliant questions, and I will see you in the next one.